right, so now we're going to be talking about chapter 4. So chapter 4 is again out of this book here, No Nonsense Quantum Field Theory. Again, I think this is a really good primer on learning quantum field theory. Also, if you like this kind of content, please hit subscribe, and you can visit my Patreon page if you want to make recommendations on books that you would like me to go over. Let's get right into this. So the Lagrangian formalism is a way by which we can begin to account for the dynamics of these fields. The Lagrangian, simply put, is an equation that will sort of give birth, if you will, to our equations of motion, right? So we can have a Lagrangian, for example, right here. This is our classical Lagrangian. When we perform something called an Euler-Lagrange equation, which we're going to derive in this video, we'll be able to get F equals ma, and that's Newton's equation right here that I have down here. Other types of Lagrangians are, this is a Lagrangian for a brick on a spring, traveling in simple harmonic motion. So we have, again, our kinetic energy minus our potential energy. Right here we had our kinetic energy minus our potential energy. My apologies for the bird in the background if you can hear him. And then we have, we can write our Lagrangian down for a swinging pendulum. This is going to be interesting later on too. But here we have, again, we have a kinetic energy term. And how do I know this is a kinetic energy term? It's because kinetic energy always has the derivative of a position in it, right? And that's going to be important for when we begin to generalize to the Lagrangian formalism. So here we have something that contains the derivative of the position. So I'll just call it that. I'll call it something that contains the derivative of the position instead of calling it the kinetic energy, because our Lagrangians can be obscure as we would like them, as we could imagine them to be. Typically they won't be, but nothing should really stop us from generalizing and saying that, well, maybe these Lagrangians are not necessarily kinetic energy minus potential energy. It might be, there might be 4 or 5 or 6 terms that don't look anything like a classical kinetic energy or potential energy term, but nevertheless it could be a legitimate Lagrangian, like what you'll see if you look at the Lagrangian for like the standard model. A lot of those terms don't really look like classical kinetic or potential energy equations. They don't, but it's a Lagrangian nevertheless. So we have this term here that contains the derivative of the position, right? The position just being an angle instead of a position on, say, like a number line. And then here we have a potential energy term, because there's no derivative of the position. There's the actual position itself. Because you have to remember, kinetic energy is a function of the derivative of the positions, and potential energy is a function of the positions. Then we have here an Atwood machine. This one's kind of interesting because it has multiple terms. We have 2 kinetic energy terms. Right? We have a kinetic energy for one mass and the kinetic energy for the other mass. Then we have potential energies for these masses, and then we have potential energy that's associated with coupling between the two. And so these are just some examples of Lagrangians. What exactly is the Lagrangian though? So Lagrangian, simply put, now that we've seen some of these examples, is L. We typically call Lagrangian L. I'll make it look like L. And it's a function of 2 things, right? It's a function of position. Position's a function of time. And it's a function of the velocity of the position, which is also a function of time. And if those 2 things are functions of time, then time is also going to show up in the Lagrangian. Right? It doesn't explicitly show up like it does in these examples. But so oftentimes what you'll see is that the Lagrangian is kind of just a function of these two. So position, so the Lagrangian is a function of positions and velocities. In other words, I give you a position and a velocity of something, Lagrangian will give me a value, right? So you could sort of think of this as you provide a position and a velocity of something. Here's our Lagrangian box. You input these two things, and this will output some number. Okay. Now the idea here, a fundamental idea here is that we can. So if the Lagrangian is a function of position and velocity, we can have our axes. Here, say, is our x-axis, and here is our x-dot axis. Right, so you pick any point on this underlying grid here. Say I picked this point right here. So that would be associated with, actually, say I picked this point right here. That would be associated with this position and this velocity. And so the value for our Lagrangian, say this is the value for our Lagrangian axis, might map onto right here. Right, so like right here, I'm going to try to draw 3 dimensions. Not really good at drawing 3 dimensions here. I can do it like this maybe. I'm not going to bother drawing in 3 dimensions. But you could see, and so if I picked a point right here, my Lagrangian might be right here. Right? So, right there. And what we build up is something that looks like a field over this grid, right? So say my field looks something like that over the grid. This is very, very interesting to us because we're thinking about quantum fields, right? When you learn the Lagrangian for the first time, this is sort of the intro to a course that you would typically call classical field theory. And that's what this section of the book goes into. Lagrangians are fields, right? Because they're functions of 2 things, the position and the velocity, you can build an overlying field out of that. Now the idea here is that, the next idea here is that I'm going to erase this and just consider our field now. Here's our field that we've built up for Lagrangian. The Lagrangian, this is not a field of space and time, right? Like we've been talking about with our previous fields. This is a field of position and velocity, okay? So every point on this field is associated with a position and a velocity, not with positions and time. That's important. So we have That's important to note because this is what's called phase space. Now you'll come across this term quite frequently. So what I'm going to do actually is I'm actually going to erase this, and I'm just going to draw a little summary here. So if we're considering a space in which its underlying structure depends on space, it depends on positions, or space and space and time. So if this is what our field is over, right? We can construct a field at every point in that field. We have some number or some vector or something like that. This is going to be what our classical fields are going to be like. Right, so these are like in the fields that we've been talking about previously. If we're talking about space and velocity, right, so this is phase space. And this is where this realm here is where Lagrangians work their best, because again, they're functions of these things, and that's why they're called fields. Now, I'm going to draw the field again. I'm going to draw the field. Here's our field. Well, now, okay, so here I'm going to say this is our phase space. Right, so here's our phase space. And actually, I want to draw this a little bit better because I want to get a point across here. The idea, the crucial point here is that suppose this is what our field looks like. And suppose this trajectory here along or within our field, suppose this trajectory here is the lowest trajectory within this field, right? So in other words, if you go this way or this way, we do nothing but increase the value of our field. So we have a trajectory. You could think of it as like the Mariana Trench, right, is the deepest point in the field at the bottom of the ocean, right? And the idea here is that that's the minimal path that that all these variables converge to on this Lagrangian, right? This is the path that's most likely going to be taken in nature. And this is called the principle of least action, right? The principle of least action goes to something as follows. The principle of least action goes as something like this. So we want to define something called an action. We want to define something called an action. We'll call it S. And then we want to say that this is the integral over all of space, three-dimensional space. And that integral, so we're integrating over all of space, so this is a field of our Lagrangian. And again, our Lagrangian is a function of, now I'm going to rewrite the notation a little bit here, because this is what you'll come across mostly in the textbooks. Q, which is a function of time, and Q dot, which is a function of time. So Q and Q dot, those are merely just labels, or not labels, but we have one as a position, Q, the other one is the velocity of the positions, or the change in the positions, which is the velocities. And these two are the arguments for the Lagrangian. Like we've been saying before, this is just really just a change in notation, because you're going to see Q's quite a bit in the books. So we take this Lagrangian exists all across the field, okay? This is a function across space, as we've established earlier. Down here, it's a field, right? It's not exactly a field in the sense that it's a field of space and time, like we've been talking about, but it's over phase space. And the idea is, again, that the trench, if you will, in this field is the path that's taken, the path that's most likely to be taken. Okay? And so we integrate this over, actually we're not integrating over time, or over space. What am I thinking here? We're integrating over time. So as time goes on, right? So what we're doing is, as time goes on, we are taking our Lagrangian and we're going to try to find its minimal point, right? So we go from time 1 to time 2. And this is what we're defining as the action. The action, again, is the integral of the Lagrangian. The Lagrangian, again, is a function of space, of position and momentum, if you will. And we want to find the path, the Lagrangian, the point, or the path at which the Lagrangian is minimized. And the way we do that, right now we've only really described the action. The action, when we consider the derivative of the action, and we set that equal to 0, this is the principle of least action. Okay, this is an extremely, extremely important principle. I believe it was Richard Feynman who said that he thought that one of the most extraordinary claims ever made in science was this principle. He thought it was so weird how nature really just abided to this principle. And on the face of it, this is a very, very arbitrary principle. Like, there really is no physical basis by which you can make this claim, but the claim was made nevertheless. And subsequent theories have been shown that this is true. Right? Not theories, but subsequent experiments have shown that this is true. And so what does this look like? What does this look like in terms of our Lagrangian? It looks like 0 equals the change in our Lagrangian. Like this. And just to be complete, like that. The reason we have Q, so the reason we have Q is that when we go back here, what I should have done is I should have labeled, these are positions of our different these are positions of our different components. Especially when we consider an Atwood machine, because an Atwood machine has two moving parts to it. It has a heavyweight and a large weight. And so the Q's generalize that. And typically you'll see an I right here. And the I goes from 1 to however many moving parts you have in your system. Right? So if you have a very complex system with a ton of moving parts, say with 20 moving parts to it, then I is going to run from 1 to 20. Okay? This is just a way of compactifying our notation. Okay? So the change in this here equals 0. Right? This is the principle of least action. And what we can get from this is something called the Euler-Lagrange equations. Now, I realize that I'm already 20 minutes into this, and what I think I want to do here is I'm going to tell you straight up, deriving the Euler-Lagrange equations is not hard. It's not difficult at all. And you can find it in tons of places online and on YouTube. And so I think what I want to do, this is going to be hard for me to do, because I think I would like to go over the deriving this again for you guys, but at the same time, I want to get to the material sooner, the interesting quantum field theory material sooner. So what I'm going to do is I'm going to write down the Euler-Lagrange equations, and if you're interested in me deriving the Euler-Lagrange equations, you can go onto my Patreon page where I will have a video of me deriving it, okay? So what the Euler-Lagrange equations look like is basically this. This is one equation where we have the derivative of our Lagrangian with respect to our position, or positions, minus the time derivative of the derivative of the Lagrangian with respect to our momenta equals 0. This is the Euler-Lagrange equations. Again, like I've said, if you are interested, if people are interested in me deriving this, you can go onto my Patreon page where I will have a video deriving the Euler-Lagrange equation. This is a huge, one of the biggest, most important equations that come out of this principle of least action. Right? And what you're able to do with this is the machine that gets you from, or this is sort of the device or the equation that gets you from your Lagrangian to your equations of motion, right? So you have a Lagrangian and when you apply the principle of least action, once you apply the principle of least action, then you get the Euler-Lagrange equations And then from the Euler-Lagrange equations, you're able to get your equations of motion. Now let me cover what these equations of motions might look like. Well, in the Newtonian case, it was F equals ma. Right, so if we took this Lagrangian right here, and we performed our Euler-Lagrange equation on this, so we take the derivative of this with respect to this, and we took the derivative of this with respect to this, and then took that time derivative, and we found the difference between the two, then we get F equals ma. Similarly, you can perform the Euler-Lagrange equation on this and get a differential equation that describes your system. Similarly, you can do it with this, and similarly, you can do it with this. Okay, that's the power of the Euler-Lagrange equations. Now, what are the equations of motion that we're going to be dealing with in quantum field theory? Well, here they are. I'll erase Newton's equations. And these are the three big boys of quantum field theory. We have the Klein-Gordon equation. I wrote KG just for short. The Klein-Gordon equation is going to help us describe the dynamics of scalar fields. Okay. Then we have the Dirac equation, which looks like this. Again, these might look a little bit obscure to you, and we'll go through derivations of these. But here's the Dirac equation. We have a Dirac-Lagrangian, just like we have a Klein-Gordon Lagrangian. When we perform the Euler-Lagrange equations on the Klein-Gordon Lagrangian, then we get the Klein-Gordon equation, which is right here. I did not write the Klein-Gordon Lagrangian out. We'll come across, I definitely will later. I'm just writing down the equations of motion for right now. We have a Dirac-Lagrangian, such that when we perform the Euler-Lagrange equations on the Dirac-Lagrangian, we'll get the Dirac equation, okay? And this is going to describe spinor fields, right? So this is for, the Klein-Gordon equation is for scalar fields. The Dirac equation is for spinor fields. And the Proca equation is going to be for vector fields. The Proca equation looks like this, right? Again, we have a Proca-Lagrangian, and those are going to be very important for us also. Now, before I call it quits here, I'm going to go back to here. Here's our Euler-Lagrange equations. What we can do is that when we start talking about fields, we actually can replace Q with phi, because that's the value in our fields. So it's not the position of some classical object like an Atwood, or like an Atwood machine, or a component in our Atwood machine. This is a value in a field, right? So similarly, we would have to take, this would be the derivative of the value in our fields. Okay. Sorry, my dog is down here breathing pretty hard. He's been doing that. So this is what our Euler-Lagrange equation looks for fields. Okay. Not really much of a change, right? We're just, instead of having our positions, we have our field values, okay? And it's this version of the equation, or it's this formulation of the Euler-Lagrange equation that's going to help us get from our Klein-Gordon Lagrangian to our Klein-Gordon equation. And it's going to be important to know this kind of stuff because the Lagrangian fundamentally is what we're after. Okay. And sorry about that. The Lagrangian is fundamentally what we're going to be after. And so when we say, what is your field theory? This goes deep into the idea of quantum field theory. When you say, what exactly is your field theory? The theory that you put forward is going to be the Lagrangian. Okay, and what we can do with this Lagrangian is we can actually, what we're gonna do next is we're gonna look at Noether's theorem. The Noether's theorem is very deeply attached to this idea of conserved quantities that emerge out of our Lagrangians when we consider shifting our underlying fields and noting of anything that might not change when we do those shifts. But again, I'm a little bit past 30 minutes now, but I can't stress this enough that the next video is going to go over we're going to go over Noether's theorem. And you know, I won't go too deep into I won't go too far down the rabbit hole here, but the point is that everything hinges on the Lagrangian. Absolutely everything hinges on the Lagrangian. When someone asks you, what is your field theory that you're proposing, you have to propose a Lagrangian or a Hamiltonian, and we'll get into Hamiltonians later also. Hamiltonians they're linked to Lagrangians. But again, without getting too deep into the weeds here, our next video is going to be on Noether's theorem, and we're going to cover that. And so I will see you guys in the next one. Again, if you like this kind of stuff, please visit my Patreon page and please hit that subscribe button. And I'll see you guys in the next one. Bye.